Hi everyone. This video will cover the first part of lesson 10.3, which is some special unique trig properties. Okay, some relationships between the trig ratios that you maybe didn't know existed, okay, that are going to be useful to you in the long run. And then I will be doing a second video that covers this exact values piece. Okay, so there are three properties that we're sort of talking about today, and you're going to see these in the context of the unit circle when we move to that topic later on this week. But for right now, I just want you to get used to what these things are really saying. So the complementary trig property, also known as the complements theorem, here's what it says. So over here, I've drawn a right triangle. Okay, 3, 4, 5. I've got angle A, angle B listed there. Let's suppose I asked you to find the sine of angle A. Hopefully you would tell me that the sine of A is 4 over 5. Opposite over hypotenuse, so 4 over 5. Okay. If I then jumped from angle A up to angle B, that 4, this side here that used to be the opposite side from the A, is now the adjacent side to the B. Okay. So because of that switch, if I then asked you to find the cosine of B, you would also tell me 4 over 5. So this is significant, all right? That when you switch from one angle to the other in a triangle, the sine of one angle matches the cosine of the other, okay? Now, where does the complement part fit in? Because if you remember from geometry, complement means angles that add up to 90 degrees. Well, wouldn't it be true that if this was a 90-degree angle, that these two angles here would have to add up to 90? And it doesn't necessarily have to be angles in a triangle. This will work for any two angles that happen to add up to 90 degrees. So if I was going to look at, 70 and 20, if I do the cosine of 70 and the sine of 20, notice that they match. If I did 89 and 1, I could do sine of 89, cosine of 1. You're not going to be able to see that. There you go. And those are the same. So any two angles that add up to 90 degrees, the sine of one is going to match the cosine of the other, and vice versa. If I did the sine of 1 and the cosine of 89, those would also match. They wouldn't be this same number, but they would match each other. Okay, so let's think about how we're going to write that down. And I'm going to write it in a slightly different way than the textbook does. It might still be helpful to look at, how it's written in this section in the book. But if I'm working with two angles A and B, and I know that the measure of angle A plus the measure of angle B is 90, then I can conclude that the sine of A is equal to the cosine of B. And then also I can say the cosine of A is equal to the sine of B, that you can flip back and forth between the two. Okay? And technically, this is what's called a biconditional in geometry. So a lot of the times, this is how you'll be working with it. You'll first figure out that the two angles add up to 90, and then you'll say, hey, I know this thing is true. But you can also go back the other way, that if you know these two are equal to each other, you also know that those angles add up to 90. Okay? So this theorem can be read in both directions and will be useful to you in both directions. Okay. The tangent property, I think, makes more sense to see it once we're on the unit circle, okay? So I'm just going to give it to you for right now, and then, like I said, when we get to the unit circle, I'll sort of illustrate it for you. The tangent property says that you can find tangent of an angle, and we already know that tangent of an angle is opposite over adjacent, but you can also do the sine of the angle divided by the cosine of the angle. Sine over cosine equals tangent, okay? I could show that with these fractions right here. So let's see. I've got sine of A here, and I know we already talked about cosine B. I'm not really using that for this example, but if I found the cosine of A, that would be 3 over 5. If I do 4 over 5, divided by 3 over 5, And the way this is going to work is that 3 over 5 is going to flip to a reciprocal. Actually, let's do this. This would flip and become 4 over 5 times 5 over 3. Because when you divide fractions, you multiply by a reciprocal. Your 5's cancel, and you're left with 4 over 3. Okay, so if I do sine divided by cosine, I get 4 over 3. Well, what's the tangent of A from up in that triangle? It would be opposite over adjacent, which is 4 over 3. Okay, so that was me just kind of proving it to you. It wasn't really a proof because I was using a specific example here, but just wanted to illustrate how that works. That if you've got tangent, or if you're looking for tangent, you can take the sine and divide by the cosine. Okay, the Pythagorean identity is probably going to be the weirdest one to you right now, and eventually in trig, it's going to be a really big deal for you. Maybe not so much of a big deal until next year in Algebra 2, but it's going to be an important one. Okay, this is another one that the picture is going to make more sense once we learn the unit circle. But the Pythagorean identity says this. If I take the sine of an angle and square it, and then do the cosine of the angle and square it. So you can kind of see Pythagorean theorem in there, right? Like a squared plus b squared. But for this situation, the c squared is always just going to be 1. Anytime you add together the sine squared and the cosine squared, it's going to come out to equal 1 of the same angle, okay? So let's try that again. If I'm looking at sine of A and cosine of A, right, and I'll illustrate this down here. See? The sine of A was 4 over 5, so I'm going to do 4 over 5 squared. The cosine of A was 3 over 5, so 3 over 5 squared. This is going to square both of these, so I'm going to end up with 16 over 25 and 9 over 25. And then they have common denominators, so I can just add together and get 25 over 25, which is equal to 1. Okay? So when I take the sine and the cosine and square them and add them together, it's always going to come out to equal 1. So let's look at some examples similar to what you're going to see in your homework. Okay? This first one, sine of what would equal the cosine of 30? This is going into this complementary trig property, that we have the sine of something equal to the cosine of 30. Then we have to ask ourselves, what's the relationship then between A and B? Well, they would have to add up to 90. So cosine of 30 would match sine of 60. Okay. So the next one, cosine of 27 would match the sine of what? Well, what do we know about A and B again? They would have to add up to 90. Oh, mental math here. I think it's going to be 63 degrees. Okay. If I wanted to verify in my calculator, I could do cosine 27, sine 63, and they do in fact equal each other. Okay. All right, this next one, I don't just want tan of 45 from your calculator. I want you to use this tangent theorem that we have up here. I want you to say to me that the tangent of 45 is equal to the sine of 45 over the cosine of 45. Now, we could go ahead and calculate both of those and actually divide it, but this is really what I want you to be able to do at this point. Okay? So here, this is our Pythagorean identity, and all this is trying to drive home to you is that in the Pythagorean identity, the two angles you're using are both the same angle. So if this is sine of 20, this would have to be cosine 20. Okay? And then if I take the sine of 50 and divide by the cosine of 50, that's this guy up here, that's going to give me tan of 50. Okay, so those types of questions are all over the lesson master, so you'll have to know how to do those. And then there are some trickier ones that we're going to get to here on the back. Okay, so for this first one, and actually I think quick, I'll just go ahead and jot down our properties that we need to know. Let's see, angle A plus angle B equals 90. This one I don't know is going to be so helpful on these problems, but Then we know sine of A equals cosine B. We know that tangent of theta is equal to sine theta over cosine theta. And then we know our Pythagorean identity, that sine of theta squared plus cosine theta always going to equal 1. Okay, so if I know the cosine of an angle and I'm looking for sine of the same angle, on this question I have a lot of people trying to go up and use this theorem here, but this is talking about two different angles. I have cosine of x and I want sine of x. The only property that's going to incorporate sine and cosine of the same angles would be this Pythagorean identity. So that's what I'm using here. I'm using the setup sine theta squared plus cosine theta squared equals 1. So now I'm going to replace cosine theta with 0.52. Okay. Let me go ahead and evaluate 0.52 squared. Looks like I get 0.2704. So sine squared, whoops, this is another notation for sine of theta squared. Sorry, hope that didn't confuse you. Plus 0.2704 equals 1. So now what? We're trying to get sine by itself. So to get rid of this 0.2704, I'm going to subtract it. So I'm doing this, minus 0.2704 minus 0.2704. And I end up with 0.7296. So now I have sine theta squared equals 0.7296. And then the question is, how do I get rid of a square if I'm trying to just find sine theta? Okay, well, I can get rid of that square by taking a square root on both sides. Okay, so my square root of that number comes out to be 0.52. Something went wrong here somewhere. Oh, I did a square root of the wrong number. So sorry. I need square root of 0.7296. There we go. That's better. 0.8541 is what I ended up with. We'll just go 0.85. And there's your final answer. Okay? Okay, so if we know sine and cosine, how do we get tangent? That's up here, right? Tangent is sine divided by cosine. I'm just rewriting the property here. Well, sine of x is 0.848. Cosine x is 0.530. And then it's just a matter of dividing them. So 0.848 divided by 0.530. And I end up with 1.6. And that's it. And this third one here gives you the cosine and the tangent and wants you to work backwards to find the sine. But still, I'm going to use this formula because this is my only one that incorporates all three. So I'm going to say I know tan x equals sine x over cosine x. So that means tan x, which is 2.050, has to equal sine of x divided by the cosine, which is 0.438. And then if we're trying to solve to figure out what sine x is, I'm going to multiply by this number on both sides. Okay, so 0.438 times 2.050, I come up with sine x equals 0.8979. Okay, so that's it for this part of the lesson. Like I said, you can look for a second video that covers this exact value stuff. Okay, but this will get you through the first part of the lesson master for today.